Let's look at linear transformations. A transformation T from Rn to Rm is a rule that assigns to each vector x in Rn a vector T of x in R of m. Rn is the domain and Rm is the codomain. T of x is the image of x under the transformation T, and the set of all such images is the range of T. So we'll look at plenty of examples of what I'm talking about. Let A be the matrix 1, negative 3, 3, 5, negative 1, 7, U is 2, negative 1, B is 3, 2, negative 5. Let's define T to be a transformation from R2 to R3. We'll define it by T of x equals A times x. Let's find the image of U under the transformation T. Okay, well, T of U, based on the definition, is AU. Okay, this cat that's sitting next to me and making noise, what are you doing, cat? Get out of here. Find the image of U under the transformation T. Okay, T of U is A times U, so it'll be 1, negative 3, 3, 5, 1, negative 1, 7 times 2, negative 1. That's 5, 1, negative 9. So that's the answer. That's the image. Okay, so now what are the domain and the codomain? Well, we can see this. The domain is R2 and the codomain is R3. Basically, you plug in something from R2 and you get something from R3. That's the domain and the codomain. If x is x1, x2, find T of x. Okay, we can do that one easily enough. T of x is going to be ax. So when you multiply this together, notice you end up with x1 minus 3x2, 3x1 plus 5x2, negative x1 plus 7x2. Lastly, find a vector x in R2 whose image under T is b, and this is where b is 3, 2, negative 5. Okay, so we want to solve this equation. Tx, which is ax, equals b. That's 3, 2, negative 5. Hey, we can just solve this on the Ti using REF, reduced to echelon form. So we end up with x equals x1, x2, which is 3 halves, negative 1 half. A transformation T is said to be a linear transformation if T of Cu equals CTU for any scalar C. In other words, you can pull that constant out. We say that T has homogeneity. Yeah, you can pull this constant out. You end up with CTU. Also, T of UV, U plus V is T of U plus T of V for any vectors U and V in the domain of T. T is said to be additive. Equivalently, one could say that a transformation T is a linear transformation if T of Cu plus dV equals CT of U plus DT of V for any vectors U and V in the domain of T and any scalars C and D. This is the superposition principle. Basically, you're applying the same principles we just saw a moment ago. You can break this up into T of U plus T of Cu plus T of dV, and you can pull out the C and the D. To save space, sometimes we write T of the vector xy as just T of xy. Okay, let T of xy equal x1, x plus 1, 2y, and x plus y. Determine if T is linear. Well, let's first see if T of Cu equals Ct of U. T of Cu is T of Cxy, which is just multiplied through by the C, and you get T of Cxcy. Now, if this is T of xy, then T of Cxcy is going to be Cx plus 1, 2cy, Cx plus cy. C times T of U, well, you just take this and you multiply it by C. So we end up with that, which gives us that. Cx plus C, 2cy, Cx plus cy. Notice that these are not the same. These are not equal, so T is not a linear transformation. Equivalently, one could say that a transformation T is linear if and only if all the components of T of x are of the form a1x1 plus a2x2 plus a sub n x sub n. So, for example, if T of x, T of x comma y equals like x plus y, 2x minus y, 3x, something like that. This is not the case with T of xy equals x plus 1. You can't have the plus 1 there if it's going to be a linear transformation.